Good morning. This is our project, and it's a comparison of three different artificial intelligence agents, Minimax, Q-Learning, and a handcrafted perfect agent, in a Pac-Man environment with multiple ghosts. The goal of this work was to examine how different AI paradigms behave under the same conditions and to understand the trade-offs between planning-based, learning-based, and user-designed approaches. Our team members are myself, Joshua Etherton, Ethan Sachs, and Armano Sibarik. Game environments provide a controlled and practical way to test artificial intelligence systems because they require decision-making under constraints. Pac-Man in particular is a good test environment because it forces an agent to balance planning, adaptation, and risk in the presence of adversarial opponents. Each agent must make repeated movement decisions while navigating the maze, collecting food, and avoiding ghosts. What makes this problem especially useful is that different AI methods behave very differently in the same environment. Our overall goal is to compare agent performance under consistent conditions and understand how different approaches to AI succeed or fail depending on the assumptions that they make.
Thanks, Josh. All right, now that we have been introduced to the problem and the project in general, I want to get into how the game is set up, how we set up the game, and some of the relevant parameters. So it's just a standard 28 by 31 grid for the game board. Pac-Man starts at the bottom of the board, the ghosts start at the top, and Pac-Man starts with 30 points and 3 lives. So important to note, the 3 lives, that's a little different than some of the homework assignments we did, the coding assignments we did over the course of the semester. Instead of using 1 life, we gave him 3. Starts with 30 points. Every time he makes a move, he loses a point, but if he eats a power pellet or if he eats a food pellet, he gets 10 points. And another important thing to note, we did not make use of the power pellet, so there was no vulnerability for the ghosts. So for the experiments, we kept them all the same. For every agent, ghost, board combination, we ran 500 episodes and had a max moves per game of 1,000, just in the case that an agent maybe gets stuck or there's an infinite loop in some cases, which can happen when doing experiments like this. And we tested for 2 maps, a baseline and a dead end map, and obviously uses multiple different ghosts in our experiments, which I'll touch on the ghosts next here and the maps after that. So the ghosts, we had 7 different ghosts. The first 4 I'll mention are the traditional ghosts, all the ghosts you'll see in a classic Pac-Man game structure. Blinky, Inky, Pinky, and Clyde. You can see a picture of what those ghosts look like to the left of each description. So Blinky, that's our aggressive directional chaser, the most aggressive ghost of the traditional set. But it's important to note, it's not a shortest path pursuit of Pac-Man. So it's not taking the shortest possible path. It's greedy directional pursuit, which means it prefers momentum. So if it can go in a straight line, it will. The only time it's going to turn is if it hits a block. Inky and Pinky are 2 very similar ghosts. They're both opportunistic, Inky in the vertical direction, Pinky in the horizontal direction. So what that means for Inky, anytime it can pursue vertically, so it can turn up or turn down, it will, but it doesn't do this horizontally. The only time that Inky turns horizontally is for collisions. And then Pinky, pretty much the same, just in the different, the different plane, right? It'll turn left or right anytime in pursuit of Pac-Man, but it only turns vertically for collision. And then Clyde's a mix of Inky and Pinky, so fully opportunistic. Anytime it's advantageous to turn, Clyde will do that. So we did experiments for all 7 of the ghosts against the different agents by themselves, but we also did some experiments with all 4 of the traditional ghosts together. So these 4 ghosts on the screen to mimic and exemplify a traditional classic game structure. And as I mentioned, we had 3 other ghosts. So these additional ghosts are ones we added ourselves, the random ghost, the hunter ghost, and the ambusher ghost. As you can tell by the different pictures, these are definitely custom ghosts. So the random ghost, this is our stochastic ghost, but it's not 100% random. And the reason for that is twofold. First, we had some issues when we first generated this ghost with it jittering back and forth. So that wasn't very emblematic of a true adversary. So we wanted to create a balance between it being both stochastic, but still being a true adverse agent to Pac-Man. So We made it so that it selects uniformly among legal non-reversing actions and decrease the randomness, by a factor of about 20%. So a nice balance between randomness and being a realistic adversary. The Hunter Ghost, this one's directly related to Blinky, right? I mentioned that Blinky was not a shortest path agent. It was greedy directional pursuit. The Hunter is in response to Blinky. This one is a shortest path agent. So taking the shortest path to Pac-Man possible. For the Hunter, we used unweighted BFS. So it's an unweighted BFS adversary where all the moves have the same cost. The Ambusher, this one's different than all of the 6 previous ghosts. This one is predictive, so it's not reactive. It's a predictive interceptor. So instead of moving towards Pac-Man's current position, it takes Pac-Man's current position, it takes Pac-Man's direction, and it predicts 3 steps ahead in that direction and targets that position. Again, using BFS, so another BFS adversary. We wanted to add these additional ghosts basically to evaluate the robustness of our different agents and see if these different mechanisms would glean any different results. Now into the maps. So the first map, this is your classic game map. This is a game map you'll see on any classic Pac-Man game in an arcade if you're going to one anytime soon. So you can see it's a highly symmetric structure. Lots of loops which are useful for Pac-Man to escape, makes it easier for him to survive. And multiple long corridors. We consider this to be our baseline map structure. And from the traditional map, we generated a modified version of it. We call this the dead end map or the trap map. So as you can see, there's some modifications. In the top right corner, there's a boomerang block structure that we hard coded in. In the top left, my favorite added structure, that's the pinwheel trap. That was really fun to hard code in there. Provides a good trap for the ghost to try and catch Pac-Man and a difficult situation for Pac-Man to get out of. And then at the bottom, on both the left and right side, there's a symmetrical loop trap structure. So the idea was to create a more difficult map, including more complex structures to force these Pac-Man agents to plan with risk.
Okay, for our formal analysis, we focused on 3 primary agents that represent distinct AI paradigms. The first is Minimax, which is a search-based agent. It looks ahead at future game states and assumes the ghosts behave in the worst way possible for its own outcomes. This makes it very cautious, but also strong in adversarial settings. The second is the Q-learning agent, which is fundamentally different. Instead of planning ahead explicitly, it learns from experience using reward feedback. Over time, it adapts its behavior based on what actions lead to better outcomes. Finally, we have what we refer to as the perfect agent. This is a handcrafted near-optimal agent that uses strong heuristics and planning, and it consistently performs very well and serves as our benchmark for comparison. We created several more agents than the 3 that we analyzed for our project. These would include the A-Star agent, which was an early baseline that used greedy pathfinding. It did not consider adversarial behavior from Ghost and was eventually depreciated in favor of more advanced agents. We also had Expectimax, which assumes stochastic opponents rather than worst-case behavior. Because Ghost movement in our environment is deterministic, this agent performed poorly and did not provide additional insight. We also did a winning agent, which was highly aggressive and focused on collecting food quickly. While it sometimes achieved high scores, it took excessive risks and had poor survivability, especially with the more advanced ghosts. Next was imitation Q-learning. It attempted to bootstrap the learning by using the perfect agent as a teacher and then move into regular Q-learning after observing the perfect agent. While it was conceptually interesting, it didn't add any performance and it was more complex than it needed to be. The next one was the hybrid agent. It combined multiple strategies by mostly following the winning agent, the super aggressive winning agent, and occasionally exploring alternative actions. This approach was difficult to analyze, and it didn't outperform the winning agent. We also created an evolutionarily tunable perfect agent. It was a copy of the perfect agent before, where we had fixed heuristics. We made those parameters where a genetic algorithm would go in and run the model and change slightly through the genetic algorithm the parameters and then select a genome of the combination of parameters that led to a better result, and then mutate those slightly and do it again, and mutate again and do it again, and select the best, mutate and do it again. We also tried a neural network based agent, but that really never got off the ground, being completely honest. That one was tough.
Now we will present how we evaluated the performance of the agents and summarize the main results. We used two main metrics, average score and win rate. Overall, we observed that the perfect agent performs the best in most cases. Q-learning is usually better than Minimax, but Minimax performs better in some specific scenarios, for example, the one against the Hunter Ghost. And we've also observed that the dead-end map increases the difficulty for all agents. On this slide, we can see the results on the baseline map. On the left side, we have the win rate against the Hunter Ghost. And this is the case I was talking to you previously about. Here we have the Minimax outperforming Q-learning, which shows that planning can sometimes outperform learning-based methods. On the right side, we see results against Blinky Ghost. Here, Q-learning performs better than Minimax, and the perfect agent achieves 100% win rate. This again shows that performance depends on the type of ghost behavior. Now, we introduce the dead-end map results. We can see that the environment becomes more difficult, and from the left side of the panel against the Ambusher Ghost, Minimax performs very poorly while Q-learning improves significantly, and the perfect agent again achieves the perfect performance. On the right, against Clyde Ghost, all agents perform worse compared to the baseline, but the perfect agent still remains the strongest, and this again highlights how the structure of the map affects the performance of the agent. On slide number 12, we show the results when all four ghosts are present at the same time. This is the most difficult scenario because all the agents have a much lower win rates, especially on the dead-end map. Even the perfect agent struggles here, which shows that coordinating survival and scoring becomes a much harder task when there are multiple ghosts present. To summarize the results, on the baseline map, the perfect agent performs best and the Q-learning usually outperforms Minimax. On the dead-end map, the environment becomes more difficult and overall performance decreases, but Q-learning still remains relatively strong. In the multi-ghost scenario, all agents struggle and performance drops significantly. Overall, both the type of agent and the environment structure highly and strongly influence the performance. On this slide, we will showcase an example run for the perfect agent against the Hunter and Clyde Ghosts on the baseline map. Just a little bit more. Stay with us. And then on the next slide, we have again an example, the same setup, but just on the dead-end map. So, to conclude it all together, performance of our agent highly depends on both the type of agent used and the structure of the environment. There is not a single method that performs best in all of the cases. Learning-based methods and planning-based methods each have their own strengths, and we have also concluded for future work, this could be extended by testing more maps, different environments, and of course improving the models even further. Thank you.